This is part 11 of the series Applications of Differentiation. In this part, we're going to start out by looking at the end behavior of functions. Specifically, what we're talking about is discussing the limit of the function as x approaches infinity or negative infinity. And so, we're dealing essentially with horizontal asymptotes. What is the function doing at its outermost portion? And so let's look at a formal definition. It says let L be any real number. The statement, the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, so here we have a distance from the L, which is epsilon. That's a positive displacement from that L value. There exists an m greater than 0, some distance, some other distance, such that the absolute value of f of x minus L is less than epsilon whenever x is greater than m. So, in other words, what it's saying, as our x values move out along the x-axis, where each successive x value is greater than some initial value m, there is always going to be a value where this epsilon is greater than 0 and the absolute value of the difference is going to be less than this epsilon value. So, put simply, the function is going to approach this L value but never actually rest on it. Now, it's very, very important to note what you can see in this graph. Notice that functions can cross that limit value, that L value. What it doesn't do is rest on it and become equal to it. It gets infinitely close to it, but never actually rests on it. So that's what we're dealing with here with end behavior. The same goes for the statement to the left with x approaching negative infinity. So what we're going to do is we're going to take a look at how this works in practical terms. And we're first going to look at the definition of a horizontal asymptote. So here we have the line y equals L is a horizontal asymptote. So this line y equals L is a horizontal asymptote of the graph of f if the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches infinity of f of x equals L. So again, remember, very, very critical about limits. We're not talking about what the function actually is at these values. We're talking about what value it's approaching. So it may never reach these values, but we're just interested in what the function is approaching. Okay. Well, let's put that into some more terms that we can actually find limits as x approaches infinity, which we call limits at infinity. So in this problem, we want to find out what's happening with this function as x approaches infinity. Well, the first term in the expression is a constant. So no matter what the x value is, the function is always going to be at 5. For this first term. Looking at the second term, as the x value increases, it's going to go into the numerator fewer and fewer times. So as x approaches infinity, this number is going to approach 0. So it's going to become inconsequential. So in essence, we can do a direct substitution here, and we can say that the limit as x approaches infinity of 5 minus 2 over x squared drives this to 0 and ends up equaling 5. So that was a pretty basic one. But this concept here with this 2 over x squared, where the denominator is increasing faster, is a critical one. So let's go on and look at another example. Now in this problem, we have a little bit of an issue. As x goes to infinity, we're not going to be able to evaluate this because this denominator is going to go to infinity, and so is the numerator, which is an indeterminate form. So somehow we have to figure out a way to eradicate this problem where we have both the numerator and denominator approaching infinity. And the way we're going to do that is a little bit of algebraic manipulation here. So let's rewrite this. The limit as x approaches infinity of 2x minus 1 over x plus 1. And what I'm going to do is I'm going to divide the numerator and denominator by x. So this is 2x minus 1 divided by x all over x plus 1 divided by x. Since I'm dividing by x, or multiplying by x over x, this has no effect from a value standpoint. It just changes the form of the equation. So now, if I want to rewrite this, it's 2x over x, because it's a monomial, minus 1 over x, all over x over x plus 1 over x. Okay, so we're actually transposing this limit all the way down here, and we'll pick it up at the top here. So the limit as x approaches infinity of this 2x over x is just 2 minus 1 over x over x over x is 1 plus 1 over x. Now when we actually take this limit, we have a constant here. This number goes to 0 because as the x gets increasingly large, it goes into 1 fewer and fewer times, and the same thing with this, goes to 0. So we're left with 2 over 1, or just 2. So we've eliminated that earlier nasty problem by using a little algebraic manipulation. Okay, now let's look at another example. In this problem, we have a similar situation, but what I'm going to do at this point is I'm going to divide the numerator and denominator by the largest degree term of x. So in this case, it's x squared. So the limit as x approaches infinity of 2x over x squared minus 5 over x squared. Took a little shortcut there and just separated out the terms and divided both by x squared. I'll do the same thing in the denominator. 3x squared divided by x squared plus 1 over x squared. This simplifies to 2 over x plus 5 over x squared all over 3. X squared over x squared is 1 plus 1 over x squared. And as I take the limit as x approaches infinity, this number goes to 0, this number goes to 0, and this number goes to 0. But as you can see, this is 0 over 3. 0 divided by anything is 0. So 0 over 3 is 0. All right, let's move on to another example. Here both the numerator and denominator have the same degree, so we'll do the same technique. So it's 2x squared over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. So this value is going to go to 2 and plus 5 over x squared over 3 plus 1 over x squared. Now we take the limit as x approaches infinity of this, this goes to 0, and this goes to 0. So what we're left with is 2 over 3. Not too bad. And let's do one more example. So here we have a similar example. So we're going to do the same thing. As x approaches infinity, of 2x to the third over x to the third plus 5 over x to the third over 3x squared over x to the third plus 1 over x to the third. This simplifies to 1 plus 5 over x to the third over 3 over x plus 1 over x to the third. And when we take the limit as x approaches infinity of this quantity, this goes to 0, this goes to 0, and this goes to 0. 2 divided by 0, 0 goes into 2 an infinite amount of times, so this limit does not exist. So let's go on to another example. In this example, we have a little bit of a twist with the radical here, but we'll get to that in a second. So let's take the limit and divide the numerator and denominator by x. Limit as x approaches infinity of 3x over x minus 2 over x divided by, now we've got to get an x inside the radical. We're going to use the fact that x equals the square root of x squared. The square root of anything squared is itself. So we have 2x squared divided by x squared plus 1 over x squared. So that's all we did, was just divide the denominator by the square root of x squared. And we took advantage of the property of radicals that says the square root of x over the square root of y equals the square root of x over y. So that's all we did down here. So this gives us 3 minus 2 over x over the square root of 2 plus 1 over x squared. We take the limit as x approaches infinity of this. This goes to 0, this goes to 0, and we're left with 3 over the square root of 2. Now we're going to look at the exact same function, only this time we're going to take the limit as x approaches negative infinity. Now I've gone ahead and rewritten the function and divided the numerator by x. And I wanted to point out that you'll note that there's a negative out in front. Because we're going to the negative side, all these x values are negative. So I don't have to put a negative sign in front of these x values. But down here, when I divide by the square root of x squared, that square makes this negative x a positive x. So I have to use this negative to force this value to be negative. And so that's why there's a negative sign out in front here. So this becomes 3 minus 2 over x over square root of 2 plus 1 over x squared, negative. When I take that limit as x approaches negative infinity, this goes to 0, this goes to 0, and what we're left with is negative 3 over the square root of 2. So here we have a function that has two different horizontal asymptotes. One to the right in the last problem was positive 3 over the square root of 2, and this one to the left is negative 3 over the square root of 2. If that was a little confusing, go back and relook at why we forced this value negative, because of this negative x being made positive by that square. And now let's go on to the next section.